Good morning, everyone. Today I'm going to talk about our methodology to estimate the power dissipation of an end user application on the RTL. My name is Magdy El-Moursy and I'm a senior engineering manager at Siemens EDA. Here is a list of items in our agenda. First, I'm going to make an introduction about software, hardware, co-development methodology we are adopting. Then I'm going to talk a little bit about the power dissipation in general in digital circuits and how to evaluate it. Then I'm going to talk about our what we call run fast, run accurate mechanism for hybrid emulation. Then I'm going to talk about our sampling mechanism to achieve this determining the power for a real-time application, for a real end-user application. Then I'm going to talk a little bit about automating our flow of execution. Then we are going to touch base on the power profiling and power analysis. Then we need to compare our results with a real hardware, as I'm going to discuss in part of my presentation. Then we are going to extend this to the performance of the circuit in terms of the CPU utilization, and then see some of the results and see how we can easily change our platform, do some changes in it, and reconfigure it, and finally conclude the talk and get some question and answer. Then let's give it a start with some introduction about our methodology for software, hardware co-development. Then in this first section, we are going to talk a little bit about our reference platform and our methodology for co-development of the software with the hardware. Actually, in our methodology, we are targeting to run a real-time an end-user application on a full platform. And what we mean by an end-user application, we are targeting an application which would run exactly as it is in the hardware in our simulation emulation environment. Then our application should run as it is, between the hardware and the software, between the hardware and the virtual model. Then we need to boot a real operating system, either Android or Linux. We need to install the software onto the operating system, and we have a full stack of the software, including the drivers, the kernel, and the firmware. And we need to run all of this also on the RTL in order to get some information about the power dissipation and performance in terms of the CPU utilization of the circuit. As I said, we can run this in emulation based, the FPGA farm, or simulation based or FPGA prototype. And what we claim to do is that we are able to run this from the day one. We have a reference hybrid platform on which you can boot the OS, run the software, and then you can convert to the RTL and determine the performance information, as we can see in the remaining of the slides. Actually, our methodology involves many tools and many mechanisms. Then we have what we call the digital twin PAVE 360 with its Veloce system interconnect. We have Vista, which is used for complete virtual platforms. We have our Veloce Hycon, which has the hybrid connection between the virtual platform and the RTL. and we have the Veloci, which is a software with a real hardware FPGA farm to be able to put a huge circuit like a processor or a complete SoC on it and simulate or emulate and determine whatever performance statistics you would like to determine. Then our methodology and set of tools includes modeling peripherals and devices which are not electronic at all on the automotive region using the PAVE 360. We can model devices on the TLM level, the hybrid, which contains virtual and chemio and RTL as well. And we can run all of this from day one, as I mentioned. And our application for now, or for this presentation, is automotive or autonomous driving software application. Our methodology and verification mechanism for the power use case is scalable. That means we can make changes in the software easily, and we can also make changes and configuration in the hardware easily. Then we are looking here to change, for example, the number of core used for the hardware, and see, after running our whole flow, see how this is going to reflect on the activity and accordingly onto the power dissipation of the circuit. Our target is to run, as I said, end user applications, which runs on the hardware for tens of seconds pre-silicon. And we need to determine the activity to profile this application. We need to define the area of interest. Then we need, after defining the area of interest, we need to take this into a power tool to determine the power dissipation in watts. Then our methodology requires knowledge about how to run the application, how to extract the information from the operating system and the driver, and it also includes identifying the area of interest. It includes using sampling mechanism and the calibration mechanism. It also involves using different tools like Veloci Hycon as a software, Veloci Strato as a hardware, Veloci Power App, and Power Flow for the power dissipation. Let's first understand where the power dissipation problem comes from. What is the challenge in determining the power dissipation? And this needs us to understand the sources of power dissipation. In digital circuit, and here I'm talking only about digital circuit because analog circuit is a completely different story. In digital circuits, there are three main and only sources of power dissipation. You have the short circuit power, you have the leakage power, and you have the dynamic power. Short circuit power is well accepted in academia and industry to be less and much less than 20% of the total power dissipation of the circuit. Then no one is interested in determining the short circuit power. For the leakage power, it completely depends on the size of the circuit. Then it is independent of the application or the activity which is done on the hardware. It only depends on the size of the circuit and the technology used, because this kind of power dissipation is dissipated whether you are switching or not, whether you have an application to run or not. It just dissipates because you connect the power supply to your circuit, and it is independent of the application. The most interesting source of power dissipation in digital circuits is the dynamic power, because this is the main source and this is the part which we can control through either playing with the hardware or with the software. The challenge with determining the dynamic power dissipation, that the equation is so simple, as we can see it here. It is alpha, or the activity, multiplied by the capacitive nodes multiplied by the voltage source squared multiplied by the frequency you are going to run the device on. Then, however, the equation is simple. We can see here it has 1, 2, 3 terms which are completely hardware dependent: the capacitance, the supply voltage, and the frequency. Then you need information about your circuit to determine in a good extent and to a good accuracy the power dissipation of the circuit. However, there is alpha in this equation, which plays a very important role, because if alpha equals 0, that means you don't have any activity, you don't have any dynamic power dissipated. And if alpha equals 1, you have the maximum power dissipated. And alpha is between 0 and 1. But this fluctuation or change or variation in alpha make a lot difference, because no one can design the circuit and determine the power based on the maximum power, because it is a lot and it is not realistic. And also no one can rely on like using any heuristic value of alpha like 0.5, because it is, again, it is not realistic. The problem with the dynamic power equation is that it depends on the hardware, as we said, and also it completely depends with linear equation with the activity, which means the application and how much the capacitances are switching. And this could not be determined but by determining the switching and the activity and the software running on your hardware. And that's why determining the power, the dynamic power, is challenging. You need information about the software, and you also need information, detailed information about the hardware. How we do this? How can we determine information about the software, the real software, the actual software running, and also the hardware, and combine them together? This is the challenge. What we do, we use a stimulus. Our stimulus is, as I said, and from the title of my presentation, is a real application running with the operating system, with the whole stack of your software, including everything, including the application itself, the kernel, the driver, the firmware, the middleware, you call it. Everything is included in order to get a realistic stimulus. We have the RTL available, and we have a virtual model of this RTL of our design. Then we use a real stimulus in order to stimulate the virtual model, in order to know the activity, and we switch from the virtual model to the actual RTL model in order to inject those activities into the RTL to determine the switching and alpha of each and every node. Then we can determine the power of each and every node of the circuit. Also, as you can see here, we need information about the technology, because the capacitance VDD would depend basically on the technology. Then we have the libraries we are going to use. We do some sensitivity analysis to know how changing the library would change the power. We target a specific library and we use it with the power tool to determine the real power of the circuit, reported in a very nice report as shown here on the bottom, and we can extract the power. Actually, running this for long would take a lot of time, and that's why the top graph is important. We run our software, the end user application, on a virtual model with a mechanism called run fast. It's a virtual model, then it is fast to a specific point of time, t0. Then we switch to accurate, which means switching to the RTL of the design. Then we run it again for some period of time to determine this power dissipation of this short period of time. And then we end our emulation simulation. Then we run it again from the beginning to another point T2, T1 in order to determine the power of the T1. And we repeat it again and again to determine the power on different points. Then we connect those points to determine the power profile using our run fast, run accurate mechanism. Then from the previous slide, run fast, run accurate is a very important key factor and mechanism to be able to achieve the power profile. Then let's talk a little bit about run fast, run accurate. As I said, if we take this application, we have a specific application coming from a specific and real customer. And the application runs, it is a DAS application, it is automotive application for auto driving, and it runs in real hardware for 30 minutes. Actually, in order to emulate this application on the emulator with hardware acceleration, not with the simulation, with hardware acceleration, the emulation of 1 millisecond would take 30 minutes of execution. Then in order to run 30 seconds of our application, we need 2 years in order to determine the whole activity. Then this is not realistic. Then what we do is that we run the application on a virtual machine, as I said, and run it until we need to switch to the accurate. We switch to accurate, and then we determine the power and run it. We run it for some time, short period, on run accurate. We determine the power, and then we close the emulation. And we repeat this again for another point and for the third point until we can get the power profile of the application for the whole application. Then, as I said, we have a full stack. We have a real end user application, which is a DAS automotive, and it runs on the virtual machine. Then we can switch using our run fast, run accurate mechanism to the RTL at the point of interest to collect information about the power, and then we take this information of activity to the power tool, which in our case it's Power Pro, to determine the power dissipation. Then let's talk a little bit about this sampling I mentioned, this sampling mechanism I just mentioned. Someone would tell me, okay, you are determining the power at only points of time like T0, T1, T2, T3, and so on. And you are not determining the power for the whole run of the application. And this is not accurate enough because you need to determine the power at all points or with higher granularity in order to get a good sense of the real power dissipated. And let's examine what and how this is being done on a real hardware. On a real hardware, and here I am showing a schematic of a real hardware device used to measure the power dissipation. Looking at the schematic and the details of this schematic, you will find that any power measurement tool measuring the power on a real hardware, it measures the current running or drawn from the voltage source or from the voltage supply for some specific period of time and average this current and store it in a register after converting this value, this average value from analog to digital. And then the concept of sampling the current, which gives you the power dissipation if you multiply it by the VDD with some sampling interval and running and getting the power and current only for a small sampling period is what really happens on a real hardware. Then our methodology matches what is being used to get the power for using real board on a real hardware. Actually, Veloce as a mechanism to speed up the emulation has another mechanism of a capture ratio where you can skip some of the cycles, and someone might think that this is a good idea to profile. Yes, it is good. However, if you use a mechanism to ignore some of the cycles, this might give you less accurate information about the power, because the power tool requires all information during a specific period of time. Then you need to sample the current or the power for many cycles in order to measure a meaningful value for the power. Then increasing the capture ratio to like any value like 4 or 8 or even 1024 would speed up profiling the power. However, it is not going to give you an accurate value for the power dissipation. Then we chose to do it the sampling mechanism using the sampling period and sampling interval over like ignoring some of the cycles and just determining the profile of the power. Now let's talk a little bit about automating this flow, because this flow needs automation. Otherwise, it might not be useful for the customer. Actually, we have a script, a tickle script we used with our Veloci. It's a Veloci tickle script called run.do. And in this tickle script, we use commands to do everything. It boots the operating system. It mounts the target file system to the host file system in order to be able to know about the sequence and the progress of the application. It starts the application on the target. It runs the emulation in run fast mode until we reach the sampling interval. Then it switches to accurate, which is the RTL model of your design. Then it runs it with the capture ratio of 1, then capture every cycle for a sampling period. Then it generates a tracing database, a hardware tracing database, contains all the activity of the circuit. It's a huge database in the order of gigabytes. Then it quits and closes the emulation. Everything is done here automatically without any intrusion or without any interference from the user to the flow. The flow is completely automated, and it runs and it gives you the database you need to determine the power. Then let's look a little bit about at the power profile and power analysis we did. Actually, we generated, as I said, in parallel to the emulation, we generate a database, a tracing database for all nodes of the circuit using the RTL, and we determine the activity of all of those nodes, and we capture it in this huge database. And we can use it to profile if the activity is high or low, but it could not be used to determine the power in watts as a value. Here we can see the activity of the application while the application is running and while the application finished running. And you can see here on those graphs that the activity is high while the application is running and is low. This is very good just to profile to see if the activity is high or low. Again, you cannot determine the power here as a value without taking this into a power tool, which can give you the real value of the power in watts. Then again, we run the application in run fast until the interval, the sampling interval we need. Then we switch to accurate to the RTL, and then we capture all the tracing information for the activity by switching to accurate, and we switch to accurate, and then we run it for the sampling period, and then we close the emulation. And we repeat it over and over again to get the power for different nodes. In the previous slide, we can see that the activity, how the activity would change with changing the software. Here we can see how the activity would change with changing the hardware. And that's why this is a useful mechanism for co-development of the software and hardware. Here we changed the design, we reconfigured the design from 2-core to 4-core, and we captured the activity for both of them. And we can notice here an increase in the activity by around 50% going from 2-core to 4-core design. Then this is changing the hardware or reconfiguring the hardware. As we said repeatedly in the slides, that we need to take this activity into a power engine or a power tool, which can give us the real power in watts. In our case, this tool is called Power Pro, and it is a tool provided by Siemens EDA. And the tool requires 3 main inputs. It requires the design RTL, it needs the technology files, it needs the activity database, which we generated by Veloce. Then the tool takes these 3 inputs and it runs the engine in order to determine the power reports. We have 2 simple scripts. One of them is called run powerpro.sh, where we set all the environment variables needed, the license, everything. And we have another script which is called run powerpro.tickle, and this tickle script is used to set the global variables if you like to size the design or do whatever with the design. It reads the technology library, the target technology library, which contains all the supply voltage and the capacitances of all nodes of your design. It reads the RTL of your design. It reads the activity database generated by Veloce Strato as an emulator. Then and it injects those activities into the nodes of the RTL, and which would generate a huge like database for the power values. It sums those up and generates a nice report about the average power dissipated by the circuit in a text file. And here is a sample of this report. This is a sample of this report, and we can see here that it divides the circuit into I/O memory. You can look at the details of your circuit, registers, combinational, sequential, clock. You can look at the leakage power and the dynamic power in terms of internal and switching power, or you can look at the total power. And we were interested only on the total power, but you can do a lot of analysis using this tool. In the coming section, we are going to compare the power we determined using our methodology with the power dissipation of the same application running on a real hardware. As I said, we used a real hardware, a real chip, with a real power measurement board tool. Then we connect the power tool, which is called Smart Power 2 device, to our hardware, and we run the application on it. As I said, the application runs for around 30 seconds. And after reading the data sheets of the power tool board, we can see that it uses sampling period of 1.1 milliseconds, sampling interval of 1 second, and the board contains 4-core ARM V8 processor, and it runs the same operating system, and we run the application, the ADAS application on it, and then we determine the power for the whole SoC and for the power for the CPU, and we found that the CPU dissipates around 50% of the power. Then we set up our Veloci Hycon as a hybrid solution. We set the parameters, we run the same application on the virtual machine first, and then we used our mechanism of run fast, run accurate, determine the power at the sampling intervals for the sampling period, and we draw the power graph. And here is a comparison between the real power dissipated by the hardware and our emulated power. We determine the power in nodes and we connect them. And there is non-trivial matching for the power profile using the hardware, which is the Odroid board in yellow, and the determined power in watts by our emulation in gray. Up till here, we were only talking about the power, but the customer we were targeting, he got interested to know more information about what's going on. Like he needs some information about the performance to put it side by side with the power dissipation and see how they compare. Then he needs to change the configuration of the hardware and see how the performance might look like. By performance here, we targeted the CPU utilization specifically because performance means a lot of things. And our target was to determine the CPU utilization for 2-core, 4-core, and maybe 8-core for the same application. We need to change the execution time. We need to change the number of core and see how this would reflect on the performance here or CPU utilization. Then again, we use the same flow, but this time, rather than determining the power, we would determine the CPU utilization. Then we use a very similar flow, which boots the operating system on the target, run the application, then wait until the point of interest, determine the CPU utilization at the point of interest, and then stop the simulation. And repeat that over and over again to get the CPU utilization profile for many nodes according to the time or along the time. And we use a Siemens source analyzer tool to plot or to demonstrate the CPU utilization graph. Then let's touch base on viewing the results of this. Here we can see the CPU utilization during the application execution visualized using source analyzer. This is for 2-core. Actually, the sorcery analyzer requires a common tracing format to be used. Then we generated the CPU utilization using a Linux utility called cat procstate, and this gives you some information about the number of cycles and how those cycles were spent during the execution. Then you need to do some calculations for the CPU utilization. You need to determine those cycles for 2 different points and subtract them, and then determine the idle time, and then you can, from the idle time, you can revert it or invert it to get the utilization of the CPU. And we used a utility to convert this raw data into the common tracing format and then display that into our source analyzer. Then here we can see the CPU utilization for running this ADAS application on the 4-core hardware design, and we can see that the utilization is very high, almost 100%. Then, okay, the customer would like to see how this might look like if we go from 4-core to 8-core. And the outcome was very astonishing and surprising for everyone. We increased the number of cores from 4-core to 8-core. And we were expecting one of two things. Either the application will finish early, or the utilization of the CPUs will drop down and the application would end at the same time. But neither of them happened. We found that with the 8 cores, still the utilization is very high, beyond the 80–90% for most of the cores, the 8 cores. And rather than the application finishes in a shorter period of time, we found that it finishes in a longer period of time. Then this is completely nonsense. In the previous slide, we were using 4 cores. Here we are using 8 cores. We have a higher computational power. Then we should be able to finish the application early or utilize the CPUs less. Why it took almost the same utilization or very high utilization for all cores, for all 8 cores, and it took longer time to finish. And when we looked deeply into the application, we found that the application, because it is a pattern recognition application for auto driving, it has some skipping mechanism for the frames. It gets the frames from the disk, then start to process them in order to make a pattern recognition, to recognize the whatever it passes through from the camera. We have a camera taking the picture of the road, and it recognizes the cars and people around. Then it takes those frames and processes them. And it has a skipping mechanism in order to cope with the frame rate which is coming from the camera. And when we used 4 core only, all 4 cores were highly utilized, and the application starts skipping a lot of frames and images. But when we look deeply, we found that when we use 8 cores, the skipping mechanism reduces a lot, and the application was able to process more images and keep tracking with the images for longer time. And this would translate to a higher quality of service from the application. In order to validate these results, we added a mechanism inside the application to only use 4 cores at a time, and not exceeding only 4 cores, which we call it affinity. Then we use the 8 cores on the hardware configuration, but the application is not allowed to use more than only 4 cores at a time. And we got this very, again, interesting graph. Now, because it uses only 4 cores, again, the skipping rate increases again, and the application finishes early again because it skipped a lot of images, and the utilization now dropped. The average utilization dropped because it is not using the 8 cores simultaneously, which is very interesting. And from all of this, we can conclude that you can play with the application and the hardware simultaneously and learn a lot of things about how the performance of the application would change with changing the configuration in your hardware. This is running another application for also 2 core, 4 core, and 8 cores. Now, changing the platform. As we said, we have a very convenient utilities and commands to reconfigure your platform. This is called the Hycon configure -- interactive, where you can do it -- list in order to give you all the list of things you can change. You can change the number of CPUs, you can change the general I/O you are using, or the general interrupt controller you are using. You change the interconnect model you are using, or the interconnect bus you are using. You change the memory. You can do a lot of changes in your platform, either from the hardware point of view or from the software point of view. And the changes and reconfiguration here are very convenient and easy. As you can see here, this is the output of running config configure the dash interactive, and it gives you a prompt to easily move from, like, you can define, I need this Cortex, ARM, whatever, 2-core or 4-core with number of clusters. I need this GIC 400 or 500, whatever. Then changing the hardware is easy, and also the software you can change, like moving from Android to Linux and so on. Also, installing any software is very convenient. We have a UART terminal to the target system, in which you can, and as I said, we mount the target drive or storage to the host drive. Then you can move files and packages into your target, and you can install them very conveniently and easily. Then you can install your software easily, and I used to get a new version of the software from the ADAS provider and just install it in minutes and see the new results like in hours. Then very convenient, very easy to achieve. Last but not least, here I am showing some parts of the tickle scripts we create in order to automate the flow. This one on the right is for the power, and the one on the left is about the CPU utilization. And if you'd like to change, for example, the sampling mechanism, the sampling period, or the sampling interval, or the time to boot the OS because you are using another OS, you just need to change the values in this script very easily, and you can make them suitable to your operating system, to your application, or to your setup. I believe by this, I need to just summarize and conclude my talk. Here in this presentation, we presented what we believe is a very unique methodology to determine the power dissipation in watts as a value for an end user application, and we target automotive here for an automotive customer. We were able to determine the power dissipation for this application running on a real model RTL model for the design, using a realistic activity and a realistic specific target technology. And the mechanism and the methodology is using the sampling in order to get the power profile in like hours and days rather than years, to get the power for such end user application running on an operating system on the RTL. We use the Veloce hardware accelerator as our emulation engine. We use our Power Pro as our power tool engine to determine the power with the technology activity. And we can also extend it to the performance and put the performance metrics side by side with the power profile. And with this methodology, we can, as we can see, we can change a lot of things on, or whatever we need from the software stack. Like we can change the driver, we can change things on the end user application and see how it reflects on the analysis and the performance. And we can change also the hardware in terms of reconfiguring it to different cores or different processor, and we can determine the effect of this on power and performance in hours and days rather than years. Thank you for listening so far, and I will be very entertained to get some questions about my presentation. Thank you. Any questions so far?
It looks like we have 2 questions in the chat box, one from Chuck and one from Brandon, if you want to start with those.
Let me check. I'm trying to find out how to see the whole chat. I only see your chat.
I can read it to you. We have Chuck ask, can Questa be used to generate the activity database?
Yeah, Questa could be used. However, Questa as a simulator, it is slow. Once you switch with our mechanism from run fast to run accurate, and you put the whole RTL for many cores like that, it is killing. Then you can't run the application with enough number of cycles and get the activity. It could be used, but for such large design, it's going to take time.
Great. And then our question from Brandon is, slide 29 showed a graph of the real versus emulated predicted power over time, but without any horizontal axis or error calculation. How close was the predicted versus measured power?
Yeah, we achieved like 80%. We did the graph as a normalized graph, but the error was around 20%. Does this answer your questions?
We have another one. Brandon says, yes, it does. And Chuck said, understood. We have another one. How typical customer calculates alpha pre-silicon? What about startup that they don't have real data?
Okay, they use test benches. Okay, what's being done right now is that they are using, like, if you have an application or a benchmark, they use whatever benchmark they believe that it's going to give you the maximum power, and they use it over and over again from a generation to generation. But in order to have the alpha or the activity of a real application, we didn't see that much in the industry.
Okay.
I start seeing the questions now. Yeah.
Okay.
If I understood it correctly, you run in fast mode based on the virtual model of the DUT and on RTL in accurate mode. Yes. If this is correct, how do you keep the virtual model and the RTL in sync state after, let's say, 1 minute of real-time application? Very good question. Yeah, we are not running them in parallel at all. We are running in virtual model completely until we need to switch to the accurate model or the RTL. Then what we do is that whenever the time is important for us to switch, we read the states of the virtual model, the whole state, everything, and we inject those states into the RTL, and we stop the clock in between. Then we stop the clock of the emulator, we read the states of the virtual model, and then we inject those states into the RTL, and then we enable the clock again. Then we are not running RTL in parallel, because RTL will never come up to speed of the virtual model. The virtual model is quick, it boots the operating system very quickly, and it initializes the application, it runs the application quickly. But whenever you need to switch to the accurate by the mechanism I just described. You stop the clock of the emulator, you read the states of the virtual model, then you inject those states into the RTL, and then you enable the clock again. I hope this answers your question. Good. Any more questions? Is the run fast, run accurate switch based solely on timer, or can it be triggered by specific events? Again, very nice question. Yeah, whatever you can trigger in the emulator in Veloci using events, using timing, using whatever, you can use it. However, in our case, we were interested to compare what we are doing on simulation emulation with a real hardware. Then we were interested to profile the power of the whole application for 30 seconds completely. Then we were not interested in a specific trigger to trigger the switch from run fast to run accurate. Then we wanted to have the profile of the power in general in front of us and see how much power this application would dissipate and how this power is going to change over time and how this is going to change with changing whatever, as I said, operating system, maybe we change the application, maybe we change on the hardware. Then we were not interested in any other trigger from a trigger event other than only the time. Then we based our solution on the time and we make it fixed. And we wanted to compare the power profile, the graph for the power of the hardware with the RTL, and that's why we based our scripts on timing. But you can use any trigger inside the tickle script of Veloci to trigger the switch from fast to accurate. Good. You are welcome. Any other question? Okay, I don't see any more questions. Does this mean that everything should be clear enough?
Yes, if there's no further questions, we can conclude this session.
Great. Thank you very much for listening to me, and see you around in DivCon.
Thank you. Have a good day.
You too.